Ya, Assalamualaikum warahmatullahi wabarakatuh. Alright, for today's lecture, we are going to continue on steel beam design. This is the second part of steel beam design. The learning outcome is at the end, you should be able to analyze and compute design resistance for a restraint beam. From a previous lecture, we have covered on the determination of design shear force and design bending moment, and also the selection of section. From today's lecture, we are going to continue step number 3, 4, 5, and step number 6. Let's recap from previous lecture, design shear force and bending moment. The beam section provided is adequate when the design shear force is lesser than design plastic shear resistant, and also the design bending moment is lesser than design plastic moment resistant. Okay, in today's lecture, we are going to calculate on the VPL-RD and also MPL-RD. For the selection of the section based on the appendix at the back, page B6 to B7, you need to extract all the design data in terms of the dimension and also in terms of the properties of the section. Alright, and also from the table, so nominal value of yield strength and ultimate strength is given in table 3.1. It is depending on the steel grade that you use. Okay, so let's say we are using S275, then our Fy is 275 and Fu is 430. If our thickness is the thickness of the flange and also thickness of the web is lesser than 40 mm, then we are going to use this column. Okay, so let's move on into classification of the section. The beam section can be classified into four classes, which is class 1, class 2, and class 3, class 4. For class 1, it is when the stress is equals to Fy at the whole cross section. It means that full plastic moment developed. There is no local buckling occurring in the section, and the structure will fail when enough number of plastic hinge develop. Okay, that is class 1. For class 2, the stress is equals to yield stress. It means that the whole section is full plastic and local buckling occurs before enough rotation to permit redistribution of the moment. That is class 2. It is fully plastic, it is that local buckling will occur. And class 3 is when the stress is equals to the yield stress at extreme fiber and the local buckling occurs before full plastic moment develops. So it means for class 1 it is at the elastic part, and we are going to design as elastic moment design. And lastly, for class 4 is when the stress is developed less than the yield point. It means that the local buckling occurs before the steel yield. It is below the elastic yield point. Okay, how do we classify our section? So based on design appendix, turn to page 3, table 5.2. It is given here the maximum width to thickness ratio for compression parts. Seeing we are going to use a roll section, roll eye section. So here is our section. The C value is taken from here to here is actually the value of D, and is divided by the thickness of the web. And then the web classification. So you need to get the ratio of C over T. C just now is D value. Then you divide with the thickness of the web. And if your calculated C over T is less than 72 epsilon, then our section is classified as class 1. Okay, otherwise, if the C over T is greater than 72 epsilon, however less than 83 epsilon, then it means that our section is class 2. Similar ways for class 3, if the ratio is in between 83 and 124 epsilon, it means that the section is in class 3. If it is greater than 1 to 4 epsilon, it means that it is automatically class 4. What is epsilon here is given at the bottom. Epsilon is the value of square root of 235 divided by Fy. Fy is the yield strength of the section. Okay, so this is the web. So the web is, you have this section. So you need to classify the web and also the flange. Okay, for flange section, we are using table 5.2 sheet 2 of 3 in page 4, which is for the flange classification. So this is the flange. Okay, so we only consider the tip of the flange. The C value is the tip of the flange. So you need to calculate what is the C value. The C value is the total flange length, which is the B value, minus the thickness of the web. Okay, so here's thickness of the web minus 2r, the radius here, divided by 2. Then you get your C value. And for the class 1, the C over T value, T here is the thickness of the flange. The C over T value is less than 9 epsilon, then it is class 1. If in between 9 and 10, then it is class 2. If it is 10 to 14, then it is class 3. Otherwise, if it is greater than 14, then it becomes class 4. Okay, so here are the summarize of the classification of this section. So first you need to classify the web. The C value here is actually the depth of the section is given in the appendix. So you just take the value of D divided by TW, and if the ratio is less than 72 epsilon, it is automatically class 1 for the web. And also you need to do flange classification. So you need to calculate what is the C value here. The C value is actually the B value minus TW here, minus 2R, the radius here, divided by 2. That is the C value for flange section, and then you divide it with the thickness of the flange. And if the ratio is less than 9 epsilon, then it is class 1. Okay, so if the both web and flange is class 1, then automatically the overall class is class 1. If you get, let's say you get for web is class 2, and then you get flange class 1, then the overall will be class 2. Okay, alright, so that's all for classification of the section. So next we are going to look into the resistance of the cross section against bending moment at ultimate limit state. So this equation is given in clause 6.2.5 EC3, part 1, in design appendix page 5. When shear force is absent or low value, the design value of the bending moment MED at each section should be satisfy the following. Okay, so this formula is depending on the class section that we have done previously. So let's say we get our section is class 1 and class 2. Then we are going to use equation 6.13, which is MCRD equals to MPLRD equals to WPL Fy divided by gamma M naught. Okay, so if our section is class 1, otherwise you have to use, for class 3, we are going to use elastic values. And for class 4, you need to use uh, effective W. Okay, so where WEL and WEF correspond to the fiber with the maximum elastic stress. Okay, so normally for section, we are going to avoid class 3 and class 4. So that we are going to use this equation only, which is we calculate MPLRD equals to WPL Fy comma M naught. So WPL is actually plastic modulus. This is you get it from the appendix. Fy is the yield strength. Okay. So once you get your MPLRD, then you compare your MPLRD with MED value. The ratio of the MED divided by MPLRD should be less than 1.0 so that the checking is fast or acceptable. The section is acceptable in terms of bending resistance. Okay, so this one you need to take from appendix. So normally we calculate for WPLY in YY axis, the major axis. Okay, so next is the resistance of the cross section against shear. Due to excessive shear force, usually adjacent to the support, the beam may fail in shear. So the beam wear, which resists the shear force, may fail as steel yield in tension and compression. The formation of plastic hinge in the flange accompanies this process. If the web is too thin, it will fail by buckling in the shear zone. So you have to check what is the shear capacity of the section. The formula for shear resistance is given in appendix page 5. Here is the formula 6.18, which is VPLRD is equals to AV times Fy divided by square root of 3 divided by gamma M naught. And then you need to compare the VED value with VPLRD, and the ratio must be less than 1 so that the checking is passed. The AV value here is the shear area. So turn to page 6. Class number 3, the shear area is given as follows. For rolled I section and H section, you can use this formula. Okay, so A value is the area of section. It's given in the appendix. Minus 2b times Tf, thickness of the flange, plus Tw plus 2r times Tf. Okay, so this is the formula for shear area, and the shear area, the AV value, but should not be less than NH WTW. So you need to make sure that the AV value should not be less than this value, TW. HW is the height of the web. And the N value is given here. Take the N value as 1.0. Okay, so you need to take note the A value in the appendix is given in centimeter squared. So you need to change the unit to mm squared, because this one, all the value of the dimension is mm. Okay, and you substitute the AV value into the equation, then you get your VPL RD. Shear strength checks with coincident shear force. The VED value is less than 50% of the shear capacity. When this happens, there is no reduction in moment capacity is required. Otherwise, you need to do the calculation to reduce the moment capacity if the VED value is greater than 50% of the VPLRD. So you need to check, you need to make sure that our VED is not greater than 50% of the VPLRD, otherwise you need to reduce the moment capacity. Okay, so the coincident shear here is 0 since the maximum moment is occur at the center and the V value here is equals to 0. So this shear force does not influence our moment capacity. Okay, so next calculation is you need to check the resistance of cross section due to bending and shear. And the combination of bending and shear, where the shear force is present, allowance should be made for its effect on the moment resistance. Where the shear force is less than the half of the plastic shear resistance, its effect on the moment resistance may be neglected, except where the shear buckling reduces the section resistance. So if VED is less than VPLRD, the 50% of the VPLRD, then the effect of this effect of the bending and shear is ignored. Okay, so next we check for shear buckling requirement. Normally, in addition to shear buckling resistance, if the HW over TW, the ratio is greater than 72 epsilon over N, you have to add another equation to check for shear buckling resistance of the section. However, if this equation is not satisfied, it means that HW over TW is lesser than 72 epsilon, then we don't have to do further checking. Okay. For standard roll, beam and column, this check is rarely necessary. So normally we get the HW over TW is less than 72 epsilon, so we ignore this shear buckling checking. And next is the flange-induced buckling resistance. To prevent compression flange buckling in the plane of the web, this criteria should be met, which is the ratio of HW over TW, again the ratio, must be less than KE divided by FYF times square root of AW over AFC. If this equation is satisfied, the checking is passed. Okay, so what is the value here? The K value here, we take from here, the factor of K should be taken as follows, depending on your class. If our structure section is class 1 and class 2, then you take the K value 0.3. E value here is the elastic modulus of steel, which is 210 gigapascal. And FYF is mean the yield strength at flange. However, since we are using roll section, flange strength and also wet strength is similar, so you just take the Fy value. So here is actually the Fy value. And AW is the area of the web, and AFC is area of flange in compression. It means that top flange only. Okay, which is BTF times TF, and also for AW is HW times TW. And HW is actually the total height minus 2 times the TF. Okay, so if the equation, this equation is satisfied, then the checking is passed. Alright, so that's all for today's lecture. We are going to continue on the next step in lecture part 3. Thank you very much.